In our last section, we had the definition of the curl right here. In this section, we had divergence right here. And we said that these are 2 of the 3 uses of the del operator. Well, I want to connect together divergence and curl. And we're going to do this in the following way, that what this says down here, if everything here is what you're expecting it to be, if you take the curl of a vector field and then take the divergence of that, you're guaranteed to get 0. If you take the curl of any vector field and then take the divergence of that, you're guaranteed to get 0. There's 2 explanations I want to offer for this. The first explanation is maybe, again, kind of thinking about this as the del operator is a vector in some ways, that somehow when you do, somehow that if you think back to like chapter 12 stuff, the cross product of a vector is orthogonal. So like we have this vector and this vector, the cross product ends up being something orthogonal to those first 2 vectors. So maybe in some sense it shouldn't surprise us that if we're doing the dot product of del with something that's perpendicular to del, well, we're going to end up with 0. Now, all that's a very hand-wavy explanation because, the del operator isn't a vector in the traditional sense. It's not like the other things. But we can, so that's the first explanation. For my second explanation, we'll do it more formally here. Let's just crunch everything out. So we do del dot the divergence of the curl here. Well, so that's going to be partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, dotted with the curl. Let's copy this right down. So the first entry of the curl is partial p partial y minus partial n partial z. The second entry is partial m partial z minus partial p partial x. And the third entry is partial n partial x minus partial m partial y. So if we take the divergence of the curl, this is the curl right here, what are we going to end up with? The partial derivative with respect to x of this minus this, which is going to be partial squared p over partial x partial y minus the partial derivative with respect to x of this, partial squared n partial x partial z, plus the partial derivative with respect to y of this minus this, so partial squared m partial y partial z minus partial squared p partial y partial x, plus the partial derivative of this minus this. So plus partial squared n partial z partial x minus partial squared m partial z partial y. And so we have these 6 things here, but let's think way back to chapter 14, the equality of mixed partial derivatives, assuming everything is all the second order partial derivatives are continuous, which we said they were. So this and this, these are mixed, partial x, partial y, partial x. Those are equal to each other, so they cancel out. This and this are equal, those cancel. This and this are equal, those cancel. And so we end up with 0 as desired at the end. Okay, so this is going to, this ends up showing here that, we have this nice relationship between divergence and curl.